Welcome back to session 18. We've only got another 2 or 3 more to go. This is really a critical part of chemistry now, is where we're going to start actually looking at the amounts, how many teaspoons, how many cups, how many grams, how many milligrams, how many moles per cubic decimeter. Those are words we're going to start talking about, concentrations. This is where it starts to get into everything we've learned. We're going to start putting it into actual practice now. Okay, we're going to be doing actually calculating amounts of substances. Now, just before we get there, in the last one we spoke about a displacement reaction. Remember what we said? We said that we had this in solution, in this case it was copper, and we put zinc in and it kicked it out, and this went into solution, it dissolved, the zinc dissolved, and the copper precipitated out. That was a displacement reaction. Now, a very important part, or another important element of displacement reactions, is the halogen displacement reactions. Remember, these are the ones in group 7. They are a valency -1. They're right next to the noble gases, the inert gases. So fluorine, chlorine, bromine, iodine. Now, if you remember, fluorine right at the very top, right? Fluorine was right at the very top. This is, by the way, halogen displacement. Halogen displacement. And what we're going to talk about is these gases, how they displace each other from a solution. So if, for example, we have got let's say we've got a solution of, let's just put this down, chlorine, bromine. Can you see there? I'm just going to put in like a little thing like this. And what it means is that this one kicks out the one below. Okay? Why? Well, they are more reactive. Remember, the electronegativity of chlorine was the highest. It was at 4. So it's, as an element, it's the most reactive on that side of the nonmetals. Fundamentally, fluorine will take the electrons from anybody. Okay? It's a greedy guts, and it's going to pinch electrons wherever it can. Remember that from way back? So what we've got is fluorine is more reactive than chlorine, which is more reactive than bromine, which is more reactive than iodine. Okay, what does this mean? It means, well, quite simple. We've got a displacement reaction. So if we have, for example, let's say we've got potassium bromide in an aqueous solution, which means it's in water, it's an ionic bond, remember? So what have we got? We've got potassium ions and bromine ions. Just to recap, the bromine has taken an electron from the potassium, right? Potassium +1, bromine -1, so KBr. Now we say, okay, now let's say we put into this, we put chlorine gas, okay? What does it mean? It means when the chlorine gets into there, the chlorine kicks the bromine out. So essentially the next step would be the chlorine is going to dissolve, and we're going to have KCl, and I know we've got a 2 there, we're going to have 2 there, right? But I'm not really worried about the balancing. Just the concept, you can balance the equations. It's just basically a 2 from the other gas, from the gas that's just doing the displacing. You've got the chlorine, 2 of those, and basically what happens over here? We get Br2, gas given off, right? So the chlorine has displaced the one below. Bromine will displace iodine from a solution. Remember, zinc displaced copper, so the copper ended up as a PPT, precipitate. It went from copper +2 electrons went to copper solid, right? That's the displacement reaction of the halogens. Worth remembering, because do you know what? It comes up next year as part of the continuation of this topic. Now let's get around to this concept of quantitative chemistry. Unfortunately, it's the bit right at the end, and it tends to go very quickly. So let's look at it here, because it's going to supplement what you've been doing, and hopefully a couple of these with some examples will elucidate and clarify. There's a clear recipe to follow with this. But first of all, we have to introduce the concept. Well, I say to you, I say, okay, let us say, for example, that we are going to do a simple acid-base reaction. Acid has got the hydrogen base. I'm going to use straightforward sodium hydroxide, right? The base is the OH, the acid is the plus, remember? This is a standard acid-base reaction. What happens here is we've got, this is aqueous, all right? And this is aqueous. So what have we got in the water? We've got hydrogen ions and we've got chlorine ions. We've got sodium ions and we've got an OH ion on its own, right? Plus ones, minus ones. So there's no, remember the baby number? There's none underneath there. So we've got that. What happens here is we basically say, right, the metal does an ion exchange here, and this one goes with that one. And remember the ion exchange? Boy, girl, boy, girl, boy, girl changes and boy, girl changes. What do we get here? We get sodium chloride plus H2O. Okay, the standard one. Now, let's just rewrite this, okay? Now we say, right, HCl, aqueous, plus NaOH, also aqueous. We've worked out it goes to NaCl plus H2O. This is a given. This is aqueous, okay? And obviously water's liquid. Now, what happens? How do we know how much of each to put in there? Well, after all, if you've got an acid stomach, right, you take an antacid, essentially an alkali, which neutralizes, it's a neutralizing reaction, neutralization reaction. What is happening? Well, you are taking the acid here, right? This acid, just for the heck of it, it's red, right? It's burny. You're taking that and you're adding something nice and cool to it. How about blue, right? To neutralize out, to basically get a nice environmentally friendly green, right? This is what we're doing. We're taking away the acidity, right? You've heard of the word pH, okay? We are changing the pH, okay? But now, what you don't want to do is you don't want to go and take too much alkali, do you? Because you're going to negate the objective. Because what is your body going to do? Your body's going to say, whoa, it's too alkali in the stomach, so it starts to produce acid, and the situation gets worse and worse and worse. Because as you know, as it moves out of the stomach environment, we get the bile secretion, which changes us to an alkali situation going into the other. All the enzymes operating under different conditions. Now, we need to know how much to take. By the same token, if we are making, do you remember this reaction? It's the Haber process, the Haber process, manufacturing ammonia. Remember, whoops, I don't want it to green, definitely not. I want it to go back to my original. Nitrogen gas plus hydrogen gas going to NH3 gas, which is an ammonia gas. Now, you want to know how much hydrogen to put in. Remember, you've got these two dirty great tanks, okay? You've seen these chemical plants, refineries and things, massive tanks and pipes leading everywhere, right? That's what chemical engineers put together. Now, you need to know how much of this must I add to that. Why? Well, we're going to be using energies. We're going to heat things up, cool them down. You don't want it to be a haphazard process. What happens when you get a haphazard process? Generally speaking, chaos of one form or another. You usually end up with an unmitigated disaster. You either don't get out what you thought you should, or you get even worse, you get a huge explosion, which is what you generally in a chemical plant don't want. And let's also look at it, hydrogen. No, we don't kind of want to mess around with hydrogen because it's highly explosive, highly flammable. So what do? It's all got to be in a controlled environment, and we need to know how much of what we're going to add, because we don't want wastage, right? It doesn't help to add 4 eggs if you only need 3, because you're not going to get out the omelette you thought you were. So we need to be able to assign measurement to this, because we say, well, how much of this. How much of that? And how much of that do we need? Now, let's go back to remember these guys? Okay. I have got other colors in there, by the way. But let's take these. Here's our nitrogen and here's our hydrogen. Remember, we went through this process. What did we say? We said, first of all, that we are going to take apart the nitrogen to end up with those ends there. Then we split apart the hydrogen over here like that, right? Now we've broken them up, right? Now they can bond. But each one of those ends is going to bond with an H, isn't it? Like that. Remember that from the molecular things we did earlier with the lone pairs and the bonding. So can you see how it's all coming together? Because what are we doing? We say, but hold on a second. This is not working because one of mine has gone across because I had to add in another hydrogen so that this one can go and bond with those three and go over there. But can you see I'm stuck here? So I have to add another hydrogen in to account for this one over here to form NH3. 2 atoms of NH3. Let's just go over here. Can you see there's one of them and there's the other one, right? What did we do? We actually balanced the equation by counting the atoms. That's what we were taught right at the very beginning. You count the atoms to balance to get to the other side. So what happens here now? Well, we can now put our balancing numbers in, can't we? And what are they? We said we had one of these. There it was. Okay. One of N2, remember? One of this. Yes, it splits into two, but there was one molecule of it. Molecule. This side we had one. Can you see? 1, 2. We needed 3. Law of constant composition means that we're going to end up with NH3. You can't have anything else, otherwise you're not making ammonia. What does this mean? It needs one molecule, 3 of those, 2 of those. Remember, one of these, we needed 3 of these, right, to make 2 NH3s. Okay? Now, the rub here is that this process, you can imagine, all right, we are not, even with our current technology, we're not in the business of counting individual atoms or molecules, okay? You can imagine the processes, the costs, the whatever to do that, the technology, right? So we had to find another way, and therefore, this is where the analogy to cooking or baking comes from. In any case, you put into a recipe, remember? When you've got a recipe, what do you have? You have, let's look at it. We have ingredients, don't we? Ingredients, what are they? Ingredients. They are my reactants, right? That's what I'm going to put together, and I then mix, heat. Hey, hang on, we might be making ice cream. Cool. All right. That's what we do, isn't it? Granted, we mix in certain sequences, but for the moment, let's say we put it all in a mixer and we mix a fruitcake up. Then we end up with a cake. And what is that? That's the product, isn't it? That's what we're actually making. So at the end of the day, all we're doing here is we're going to be doing the same process. Now, let's have a look in this whole cooking, baking thing. They talk about add 1 cup of this, 1 TSP, 1 T, like that, okay? You have things like 1 pinch, all right? Then you could have 300 grams, all right? Okay, we're going to leave out pounds and all of that lot, but 300 grams. You could also have 200 milliliters. Can you see here, there's a complete mix of units. Mix of units. Why? Because it's not absolutely fundamentally precise. No, it doesn't matter if you add a little bit extra water or a little bit less. Of course it matters how much you add of it. If you add way too much, you're not going to get a cake. You're going to get a sloppy mess. Take, for example, pancakes, batter. You mix the flour, the eggs, the milk, I think, a little bit of oil, I think, and some salt or whatever. Guys can help me out. You maybe know it or you can Google it. What do you get? You mix in the correct proportion, right? You mix so many of this with so much of that and so much of that. Why? Well, let's say you put in too many eggs. What you're going to get? You're going to get a runny, gooey mess. Too much milk, same. Too little milk, what you're going to get? You're going to get like a thick, clumpy thing. In other words, the product is not pancake batter, it's something else. You could maybe use it to batter fish or bake it as a cookie, but it is not pancake batter. Right? Remember we said we've got to add it in the right proportion. Okay? Now, just to reiterate, that's our recipe. The correct proportion from the recipe, guys, that's what this is. These are the recipes. Right? One of those, let's for the moment call it 1 cup, 3 cups, 2 cups. Okay? 1 teaspoon, 2 teaspoons, 3 teaspoons. 1 pint, 2 pints, 3 pints. All right? 1 liter, 3 liters, 2 liters. I'm exaggerating here. I mean, it's not exactly like that. But what am I saying? What I'm saying is this. I am saying that, let me just leave it here. These units here, these units must be the same. Okay? In chemistry, they must be the same. Why? Because we are counting individual atoms and molecules. Remember? Like this. So they must be the same. Now, into this, we bring in the concept of the mole. Okay? Now, I know that you've been doing this in class, but let's just rehash it. The mole. What is a mole? It's from the German molecule, which is mole, and I hope my German pronunciation was right there. But it comes from molecule. Why? Because that's what we're counting. We're counting molecules, aren't we? Remember the 1, 3, 2s? We actually counted how many molecules there were. So if we can come up with something, we can convert sodium, potassium, silicon, calcium carbonate, okay, calcium bicarbonate, blah, we can convert them all to a single measure, which in chemistry we call the mole. Right? Now, as it happens, there was a guy called Avogadro. Okay? And Avogadro came up with something called Avogadro's number. And I think it is 6.02 times 10 to the 23. We'll just check on all of this. Okay. Yep, it is. Okay. What is this all about? Now, what he said is that 1 mole of anything has 6.02 times 10 to the 23 bits. Don't worry about this, okay? I know my terminology is loose, okay? 1 mole of tennis balls has 6.02 times 10 to the 3 tennis balls in it. So all it is, it's a collective measurement device, isn't it? In other words, it's saying that if this is a mole of anything, inside here it contains 6.02 times 10 to the 23 parts, right? So 1 mole of electrons contains 6.02 times 10 to the 23 electrons, right? Okay. 1 mole of bananas, 6.02 times 10 to the 23 bananas. 1 mole of sodium has got 6.02 times 10 to the 23 atoms. So if I counted all the NAs, okay, I'm going to count them up, I'm going to get that big number of them. and we just call that a mole. It's the same as a kilogram or a liter. It's a measurement of, I'm going to say mass, but it's a measurement of how many particles are in there. And you can see why we use it, because we count molecules. So this number is pretty important to us in the counting of the molecules, because it tells us how many there are, right? So we can now upscale this into actual physical values of grams, kilograms, etc., right? So the concept of the mole was that, right? Well, okie dokes, fair enough. Now what do we do with it? Well, we say 1 mole of oxygen. How many atoms are in there? Contains 6.02 times 10 to the 23 O2 molecules. O2 molecules. So 1 mole of these, okay, there are 6.02 times 10 to the 23 of those units. But that splits into 2, right? Which means 1 mole of O2 has got 2 times 6.02 times 10 to the 23 atoms. Isn't it? Because it's splitting, right? Let's just take another one. 1 mole of NH3 contains 6.02 times 10 to the 23, which is called Na, Avogadro's number, molecules of NH3. But how many atoms are there? Well, in 1 mole of NH3, what do we get out? Well, we get 6.02. Now we're working with atoms, okay? 6.02 times 10 to the 23 N atoms, nitrogens, and 3 times 6.02 times 10 to the 23 H atoms, right? Because we have to split it up, okay? Let's look at one more, all right? Sodium carbonate, or no, let's do magnesium carbonate, no, sodium carbonate, okay? Carbonate is CO3, isn't it, okay? Valency of CO3, -2, okay? So we have let's just do my CO3, all right? And I said we're going to do sodium carbonate, Na, okay, but now hang on, CO3 is a polyatomic ion, -2. Sodium is a +1, so we need to get to +2, so we need to have 2 of those. Remember those? My students called them baby numbers, those, the small ones at the bottom, okay? So if I have 1 mole of sodium carbonate, I have got 6.02 times 10 to the 23 Na2CO3, okay? Molecules, haven't I? But how many atoms? Now we have to split it to atoms, okay? We've got 2 times 6.02 times 10 to the 23 Na atoms, right? Because there's 2 in each molecule. 1 mole contains so many molecules, but atoms there's 2, right? Therefore, there's also 6.1 times 6.02, sorry, I'm thinking of oxygen, aren't I? 6.02 times 10 to the 23 carbon atoms, and 3 times 6.02 times 10 to the 23 O atoms. Okay, where does the error occur here? 99.9% there. People forget that. Okay, let's say we had, for example, an SO4 and a 2 on the outside there. Now remember, 1 mole contains 6.02 times 10 to the 23 molecules. But the atoms, there's 2 times 6.02 times 10 to the 23 sulfur, because this has to go in. And 8 times 6.02 times 10 to the 23, O atoms. Atoms. Right? So on Avogadro's number, essentially, we are saying we've now got something that we can use to quantify. That's why it's called quantitative aspects. So we can quantify now how many molecules or how many atoms are inside the chemicals that we're going to mix. So we can start to get a feeling for what? For how much to add. Because we need to know one of these and one of these does that, right? Which is great if we're doing one on one. We've just done an exchange like that, haven't we? But if it's more like ammonia, it's a little more complicated. Okay? So we have to work it out. We are now going to, in the next session, we're going to look at something called molecular mass. Okay? We're going to look at the molecular mass. The molecular mass, okay, is how much does it weigh? How much does a molecule of oxygen weigh? How much does whatever, okay, weigh? And how much or how many molecules and atoms are inside it, okay? And what I'm going to do is I'm going to show you a table that I really strongly recommend you use. It's just a method of keeping track of everything. I like to think of it as good accountancy inside chemistry. It just keeps a nice logical incremental order. And the beauty of using this table method is that as you work through it, it highlights straight away, calculate me, flashing lights, me, look, there's a big gap here, find me. It also helps to logically process the thoughts of going through it. The other aspect is it allows you to expand and extend the bottom of the table as we start adding concentrations, electrochemistry, neutralization reactions, and even when we get into oxidation reduction, we can add electrons and things when we start even looking at plating. Okay? In there, it allows us to use, the table allows us to just add on at the bottom so that we can start with the balanced chemical reaction and move through the process until we come up with the answer at the end of how much or whatever they're asking us to do, right? So we're going to look at molecular mass. We're going to look at a few items in that genre now, right? So we're going to start working out how many grams of this contain what, and eventually we'll start doing some chemical reactions, and we'll start calculating how much of what do we need to add to this to do that, whatever the objective is going to be. Thanks for watching this one. The next one, please, once again, I know, but have your periodic tables handy, just so that you can go with me and you can see the numbers I'm referring to when I talk about 1 mole of this is 12 grams, etc., etc. Okay, thanks, cheers. I'll see you in the next session, number 19.